I'm going to show you some demonstrations of simple harmonic motion. These are two different types of simple harmonic motion. There are several of them. For example, if I have a mass on a spring, notice this mass is hanging from a spring. It's suspended, and right now it's not moving, more or less. It's in equilibrium, which means the forces on the spring up and the force of gravity down on it are balanced out. But if I move it from its equilibrium position a little bit, it can oscillate up and down. It's moving in simple harmonic motion, which means if it's below its equilibrium position, the force of the spring is pulling it up. If it's above its equilibrium position, then the force of gravity is pulling it down. There's always a restoring force movement back to its equilibrium position. We'll talk more about this. These are just some demonstrations. These are three pendulums. I'm going to do the largest mass first. If I move it away from its side, notice it's oscillating back and forth in this direction. I'm going to kind of turn at an angle here so you can see a little bit better. Let's slow these down. These pendulums, if I move this large mass back and forth like this, again, it's moving in simple harmonic motion. It's oscillating back and forth at the same rate. Now, I'm going to show you some different situations here. So here I have a 500 gram mass on a spring. I'm going to have an identical spring, almost the exact same type of spring. If I put another 500 gram mass on here, again, they're not the exact same length, but they're the same type of spring. If I move them from the equilibrium position, the same displacement, I let go of them, they'll oscillate back and forth at the same rate. Now watch what happens if I move one of them a greater distance from the equilibrium position and a smaller distance. See what happens to the rate of oscillation. Notice the rate of oscillation is actually the same. They go up and down at the same rate still. But what if I put a smaller mass on here? I'm sorry, let's put a larger mass on here. Let's put an extra 100 gram mass on here. And now, if I move it from its equilibrium position, notice what happens. This mass is oscillating faster than this one. This is a slower one because it has more mass on it. Now let's do the opposite. Let's do a smaller mass on this one and put a 200 gram mass on this one. Both at rest, displace them some distance. Whoops, this is displaced too much. Let's go small and large. And notice how quickly this mass is oscillating up and down. It has a smaller mass on it. This one has a larger mass. And so this oscillation is at a slower rate than this oscillation. Let's take a look at the pendulums. Now we have three different masses here, a large mass, a medium mass, and a small mass. Now, like the springs, the masses made a difference, but let's take a look and see what happens. If I move all three of these back at the same distance from its equilibrium, let them go, notice all three masses are oscillating at the exact same rate. The mass for a pendulum doesn't matter. They're oscillating back and forth at the same rate. Now let's do this. I'm going to take this large mass and have it go a little higher. I'm going to take this mass, have it go even higher, like this. Now these masses are at different lengths. Now I'm going to try and move them all back and let go of them at the same time. Let's see which one oscillates back and forth. Notice the faster ones are the ones with the smallest length. This one oscillates back and forth faster than this one, and this one oscillates back and forth faster than this one. The masses for a pendulum doesn't matter. The only thing that matters for the frequency or the period for a pendulum is the length of the pendulum itself. And we're going to go through some notes. I'm going to refer back to these little demonstrations as we go through the notes, so at least this gives you a reference, a visual reference of what we're talking about.